Okay. Hi, everyone. So today's guest is John Yang from Princeton. So John's going to talk about, can language models resolve real-world GitHub issues? So an important and engaging topic. So John is a research assistant. He works at Princeton, and he's advised by Professor Karthik Narasimhan. He's interested in language grounding and interaction, benchmarks for LLMs, software engineering, and code generation. So thanks very much for joining us, John. There's usually a fairly active chat going on, so just ignore that. If there's anything important, then I'll raise my hand, and then you can sort of call on people as need be. We usually try to keep all the questions to the end, but if people do have clarifying questions or something like that, then you might see that pop up from time to time. But otherwise, the time is yours. Thank you very much.
Thank you, everybody. Yeah, really appreciate it. And super glad to be here. So yeah, I'll share my screen and kick things off. Cool. So yeah, as mentioned, I'll be sure to attend to questions. I'll rely on Rohan to kind of give me a heads up. But feel free to interject at any time if there's any sort of extra context and clarification I can provide. So I'm really excited today to present some of the recent work I've been sort of putting my time into and collaborating with a couple of folks here at Princeton. And the latest project that we've put out is titled SWE-bench, with the sort of question, can language models resolve real-world GitHub issues? And this project was completed with a lot of great collaborators. So to just kind of set the stage a little bit, as it seems apparent, a lot of us are really aware of the ongoing trend of language models. Like a year ago, with ChatGPT coming out, in the year since, there's been a lot of energy and excitement and a lot of advancements with respect to language models being improved, whether it's expanding their context windows, improving sort of the data that they've seen with richer pre-training corpuses, testing them on different kinds of settings, really going beyond traditional NLP benchmarks. So as a result of that, what we've seen is that many long-standing benchmarks that are maybe surrounded around tasks like common sense reasoning or like multi-hop question answering and things like this are just generally becoming too easy for today's state-of-the-art models. So what we see is, ChatGPT and of course like GPT-4 achieving like human or even like superhuman performance on a lot of these evaluation tasks. And as the trend has been in machine learning, in the past and always, new benchmarks have always been quite critical to sort of defining what these capabilities are in terms of sort of the test subject, and then sort of pushing the frontier. So especially as things are becoming saturated, there's definitely sort of this urgency and call to action of defining sort of new landscapes and new test beds for better understanding like what exactly are LLMs good at and what are they not good at, and kind of formally sort of quantifying and qualifying these things. So in that respect, in the past couple of years, there has been sort of a lot of recent work that tries to address this call to action. Generally, from our perspective, we feel like there's two sort of categories or large buckets that this falls into. The first one is sort of what we call this like potpourri style of evaluation. So what this means is, as opposed to before, where maybe you had like glue, which is like just general language understanding, or maybe you had like a common sense reasoning specific task, or like hot pot QA, which is just for question answering. What if you take a lot of these diverse tasks and kind of put them in one sort of arena? And then the language model is basically asked to is being evaluated on all of these tasks. And sort of the upshot of all of this is, by evaluating on a bunch of different NLP tasks, I can give you sort of a more holistic picture of how this model performs on a spectrum of things. So, we've seen sort of very sort of traditional work that tries to conglomerate a lot of NLP tasks and update them like superglue. We've also seen like MMLU, and then most recently, Big Bench came out this year that sort of builds upon superglue even more. It was a big community effort to get people involved and a lot of participants to sort of handcraft these really great tasks. And even more recently, we've also seen people kind of start to turn to different settings, really interesting settings like language models as agents or language models as things that can navigate the web and treat these settings as sort of evaluation playgrounds. So the second half to this is code generation. So this is a long-standing task in artificial intelligence, and it started a lot within software engineering and programming languages. But its sort of most recent manifestation, particularly within NLP, has been sort of in this format of a transduction task where I give you an input sequence that's a natural language description of what I want. And then the output sequence is just code. And usually this is for evaluating models that have a pre-training corpus that consists of both code and natural language. So that's how it's able to do that translation. While programming languages are interesting in terms of the languages that are actually covered and reflected in NLP benchmarks, is fairly siloed into Python and a little bit of SQL. So I listed a couple here, but human eval is the one that you constantly see coming up in papers today in terms of sort of the standard when it comes to sort of benchmarking these things. So taking a closer look at code generation, one of the things that is interesting here is just kind of understanding like how close is this to sort of real world equivalents of software engineering and data analysis and things that you and I are very, very familiar with and even do on a daily basis as kind of part of our jobs. And what we find is that this code contest style that started way back with like alpha code and has sort of been adopted and translated into different sorts of benchmarks is really based on this sort of single method header, along with a doc string that kind of describes, what the desired functionality is. And then there's sort of a couple of like few shot demonstrations, if you will, or really just sort of input output to demonstrate sort of like what the function should be doing. So if any of you are like really familiar with like the LeetCode platform, it's pretty much just this, right? So what are some of the shortcomings with this? Well, it's a really short problem description. Even with the solution combined, usually everything put together is just under 200 lines. It's very self-contained. So while you and I might be importing NumPy and importing pandas, defining our own modules within our code base, and then importing that functionality locally within the context of the code base and using that, these tasks don't expose any of that complexity. Also, in lieu of that, it also requires just primitive Python, right? So if I want to sort a list, or if I want to sort like a fairly complex data structure, you and I might leverage an existing function within the code base to do that, and then make sure that the code that we write follows the style of that code base. That sort of complexity and that level of understanding and requirement is not really sort of nailed down here either. And then last but not least, this is sort of characteristic of not just code contest benchmarks, but also sort of the aforementioned ones. Usually the unit tests are either synthetic or handwritten. Now, the problem with handwritten is that it's very expensive. You're paying task workers a lot of money to generate sort of otherwise fairly trivial tasks. In recent years, like people have definitely attempted to use language models to synthesize tasks, but there's always kind of the concern that like if the language model can generate the task, then arguably it could probably solve it too. So these tests are sort of like it could be said that they're maybe a bit trivial in some sense. Before I move forward, like even with the potpourri tasks, one of the issues is that having this big spread of tasks is not a great playground for either one, allowing models to demonstrate novel capabilities, or two, forcing models to like compose existing abilities. So for example, we're aware that language models can kind of create a plan and then execute it in a very closed formatter. Or if we look at a lot of these sort of prompting reasoning frameworks that have come out in recent years, like chain of thought, React, tree of thought, it's very evident that models are able to sort of perform or, mimic some form of reasoning, but then sort of having to perform a reasoning trace that might require compositions of these frameworks, like planning first and then interacting with an environment to gather information. taking that information and then synthesizing it into some solution or some next sequence of actions. It does not rely on any single one of these sort of reasoning frameworks, but rather sort of a lot of them put together. So having a benchmark that's able to capture a lot of that, a lot of these sort of needs would be really helpful. Cool. So um, basically, the inspiration for this project is we kind of turn towards like real world software engineering and sort of the software engineering research field as a source of inspiration for finding tasks and sort of defining benchmarks that can address a lot of these aforementioned issues. So here I just created a little example. On the left, what we're seeing is a diagram where each circle refers to a file within a folder of the code base, and the size of the circle refers to just the lines of code. So for scikit-learn, what we're seeing is that, this is a highly complex code base. There's a large API. There's a large set of functions that you can call and do different things with, whether it's like, and even the folders themselves sort of suggest that there's like different implementations with like SVM, covariance, Gaussian process, all these things, right? So it's much denser than just sort of the code contest style of I want you to implement this one single function. Um, in addition to this, there's a really complex dependency graph that we see here, kind of alluding to that aforementioned problem of code being fairly isolated and just primitive Python code. Here, a language model or a human task worker is not able to get away with that. It's really important to understand the structure, the organization of the code base, understanding the style, adhering to different practices, not only to get things to work functionally, but also have them be sort of stylistically correct and allow it to be palatable for your other collaborators and other sort of people working on this and using this project. And, extensive documentations, and of course, many users, right? So given this code base, like what are the potential challenges that might come up is sort of a really interesting question to think about. And to us, there are a couple things among many more that really come to mind immediately. One of the first ones is really long context. So here it's sort of a meaningful long context challenge in the sense that, it's not really just like a bunch of kind of unrelated things put together and we're asking for a model to kind of look for a needle in the haystack. This is one sort of collective code base with hundreds to thousands of files and like hundreds of thousands or millions of lines of code. And they're all kind of put together in a sort of highly intricate and sort of intentional way. Another challenge with this long context is identifying bugs. So like if there's a problem with the code base, just narrowing down like what files or what lines to edit is a challenge in and of itself. And of course, understanding functions, relationships, following the code structure and style. There's different solutions to sort of solving a problem with the code base, many more things. So I've kind of already alluded to it. Basically, given a code base, what is a potential task that we can sort of construct from this sort of really nice, natural source of organized data. And sort of to answer this question, we turn to sort of open source software development and mainly sort of inspired by GitHub. And I'm sure as all of you are very familiar with, like with GitHub, collaborative development is one of the main drivers of open source software maintenance and what makes it really successful. And the pattern that it usually goes by is that someone is using scikit-learn, runs into a bug, and then when they see the bug, they'll declare an issue. They'll say like, okay, like your matrix factorization is returning this type, but it should return this type instead. Some observed behavior of the code that sort of isn't in line with expectations. And then that's captured sort of as an issue semantically. And then what happens next is sort of a maintainer of the repository will take a look at the issue and say, oh, okay, I understand. I'm going to fix the code in that way. And then that sort of fix is presented as a pull request. So hopefully this is familiar. Maybe some of you already know this, but just kind of doing this to establish a common language. So, issues and pull requests. Cool. And then, this is sort of a direct example. grab from one of the sort of repositories that we'll talk about later on, where the issue in natural language is a user conveying what the problem they're seeing, usually involving some mixture of natural language, maybe a couple code blocks, maybe even images, depending on the nature of the repository. And you'll see a pull request that says, I've addressed this issue, and the pull request has some associated changes. So this open source software development cycle makes for a really, really good task. And this is sort of like our observation that kind of leads to SWE-bench. So SWE-bench is this new evaluation benchmark and data set that we've come up with that evaluates language models on the sort of software engineering as a task. So what this looks like in a nutshell is the language model is given an issue and then given the code base associated with that issue. So for example, like even right now, you can jump on GitHub, and if you click on a pull request with associated issues, that information is sort of present there. I have a problem with the code base, at this particular version. All of this context is then given to the language model, and the language model's responsibility is to then generate what we call a patch file. So a patch or potentially diff file is just a fancy word for a file format that is used for transforming text files from one form to another. So that's at a high level. At a low level, it's really simple. It's just a file format that indicates, given one file, I should add a line here, change this line, delete a line here. So using this sort of patch format, you can reliably modify a code base and multiple files within the code base. And the goal is a language model should generate a patch that then fixes or addresses the issue with this code base. And then the way that we can verify whether the issue has been resolved is through a series of related unit tests. Cool. So this is kind of the task formulation. And now I'm going to talk about sort of how we collect this entire data set with these components of sort of the issue, the code base, and the actual unit tests themselves. So SWE-bench is a collection of 2,294 task instances from 12 different open source repositories on GitHub. And for the purposes of putting this data set together, we rely particularly heavily on PyPy packages. So on the left, you can kind of see the PyPy packages that we use, along with sort of the distribution of tasks from each of them. Maybe there's some familiar ones there. And then on the right, what we see is sort of statistics that are kind of quantifying an issue, an average issue within the code base, within the data set. So what we see is that a task instance on average has an issue with about 195 words. There's sort of a really long tail distribution when it comes to the max. So there's like really, really long issues that we have in there. Each code base has about 3,000 files with a lot of lines, so nearly 500,000 lines. And then the gold patch is what we refer to as the fix that the PR presents. So in the next slide, I'll talk a little bit about collection, but for now, I'll kind of focus on the statistics. So the gold patch, which you can just think of as the solution to the original issue, which is sort of captured as this patch file format that we just talked about, has an average of 32 lines changed, around 1 to 2 files edited, and then within those 1 to 2 files, it changes about 3 functions on average. And then last but not least, we have the tests themselves. So these tests, they could be unit tests, they could be end-to-end, really depends on the repository. On average, we have 9 what we call fail to pass tests. So what this means is that prior to the gold patch being applied to the code base, this test was failing. But then after the fix, this test passes. So these 9 tests are really critical to qualifying whether or not the issue was solved. Cool. Great. So how do we actually put together this data set? So it's actually a fairly straightforward process with a lot of technical details I won't get into today, but sort of conceptually at a high level, it's actually quite straightforward. So what we do, starting on the left, is we pick a couple of repositories that seem like really, really good candidates. So what is a good candidate for collecting task instances? It's usually a repository with a lot of pull requests and a lot of issues. In practice, what we do is we go to a website that kind of has a leaderboard of the most used PyPy packages, and we kind of look from there. From there, we kind of select and, through some iteration, settle on a couple of repositories that we want to try sort of collecting this data from. And the first step that we do is, given the repository name, we collect all the pull requests associated with it, just like from the inception of the GitHub repository. Next, after we have the pull request data, attribute-based filtering is a step that takes these pull requests and converts each of them to a candidate task instance. So what this means is, for each pull request, we look for a couple of things. First, we look for whether there's a related issue. So not all pull requests necessarily have issues associated with them. So those are things that we can't use for a task instance, just because there's no sort of good problem description that's associated with a particular fix. The gold patch given a pull request is really easy to get. It's just sort of the associated code changes that come with it. But then last but not least are their unit tests. And for here, what we do is we look at the code changes associated with that particular pull request, and we just look at the files that were edited. And if any of those file paths have any sort of testing related keywords in them, we kind of use that heuristic to identify, oh, this is a sort of gold patch modification that's related to changing the code base. This is an introduction of a new test. And we sort of separate that patch into the gold patch and then the test patch. So hopefully that makes sense. And last but not least, what we need to do is with SWE-bench, SWE-bench relies heavily on execution. So we're not doing anything related to sort of like comparing the surface form similarity or semantic similarity. We're really focused on execution in the sense of, can this patch actually fix the problem at hand? It doesn't have to look similar. It could be a completely different novel solution, but as long as it passes the unit test and the language model did its job. So in order to do this, we set up this sort of evaluation harness that takes care a lot of the recreating of the execution environment. So at a high level, it clones the repository, it finds the correct commit associated with that issue, checks it out, does a bunch of installation procedures. And then once the model generates the patch is then applied to the code base, and then the unit tests are run. And then based on the unit test results, we can quantify, how many tests passed. And if all of the tests pass, we consider this model as having successfully addressed the desired issue. So this visualization is kind of meant to nail down a lot of the jargon and terminology we just introduced in sort of these really concrete things. So this visualization corresponds to a single task in SWE-bench. So what are the components? Well, there's a lot of metadata associated with it that is important to just kind of understanding where this task instance came from and for sort of recreating the execution environment. So these are things like the repo, the instance ID is just a combination of the repository and the pull request number, or the ID. The issue numbers are the issues associated with the pull request. It's a list of like one or more issues. The base commit, the date it was created, and then the problem statement is essentially just the issue. So this is sort of we do very little post-processing on the issue. It's very faithful to sort of the original text from that repository. And then the test patch and the gold patch are the pull request code diffs separated into test-related changes and the reference solution. So the test patch is what we apply and then run on top of model solutions to check whether the model solutions actually worked. And then the gold patch is really just a reference solution that we can use to sort of, in case we want to compare or for other things we'll talk about later. Okay, so what are kind of like the benefits of this? To go through this really quickly, since we've kind of harped on it before, this is very, very much a real world task. So as opposed to sort of code contests that are really designed for interviews, but no one really has to reverse a linked list day to day in their daily sort of software engineering duties. Here, you have a code base that doesn't just present completion or code completion as a problem, but also has these components of how do I navigate a code base and cut down a really, really large set of code files into the relevant context that I need to then actually make an edit. And as part of that, I need to understand dependencies. So it's important to not just identify the file that I need to change, but potentially what that file imports and what files import that file to understand sort of a more holistic picture of sort of the expected behavior of the implementation. Editing someone else's code, as we know, probably from our own, all have our own stories, is usually a lot harder than writing our own from the ground up. And then sort of using libraries and using imports, these are just several of the challenges. Also, SWE-bench is really updatable. So what this means is, like, as opposed to like Big Bench or a lot of these prior tasks that require human task workers, SWE-bench is really, really sort of hands off in the sense that we write a lot of these automatic functions for collecting the pull requests, the candidates, doing this conversion, extracting the unit test, and then running the execution to verify that it's usable as a real task instance. So this is good because, like, in the future, if a paper kind of claims it does really well on the existing SWE-bench tasks, we can check whether it's overfitting or whether it's sort of a real reasoning contribution by just rerunning our collection procedure to get new instances. And of course, really diverse long inputs, both in the issue and the code base. Really robust evaluation. So as opposed to before, where you might have these really semantically oriented surface form comparison scores like Code Blue, which is kind of based on the Blue score for comparing natural language generations. Or, with code contests, what you see is things like pass-it K, where K is like the number of generations, or you have like synthetic tests. They're all sort of associated issues with these metrics stemming from the fact that they're either not very practical or it doesn't come from sort of an actual human-written, you know, a purposeful test, if you will. And in this case, we really address these issues by collecting tests from these repositories as opposed to generating our own. Cross-context code editing has been harped on before, so I won't get into it again, but just sort of understanding inputs and understanding imports. And then a wide scope for solutions refers to this idea that the reference solution presents one way to have solved that task, but it'll be really interesting to see how language models, as they improve, and then potentially given different preferences from a human sort of guidance, the different solutions it might be able to come with. And we'll kind of talk about sort of that more in our evaluation. Cool. So you're probably maybe already turning in your head a lot of potential approaches to solving this problem. And we'd like to think that there's a really sort of exciting space that SWE-bench could establish in terms of trying out different methods, but then also presenting a level playing field that allows these sort of very different methodologies to be quantified and compared sort of at the same scale. But the two things that we focus on for this initial paper are sort of the most intuitive baselines that we can think of. So these are not very complex systems, very straightforward. It's essentially just prompting and document retrieval. And before I get into sort of the complexity at a really high level, it's very straightforward. What we do is we do some really basic retrieval using sort of sparse retrieval like BM25 to extract the relevant code files with respect to an issue description. And then we prompt a model with those code files along with some instructions on how to generate a patch, and we get an answer, and we get a patch generation, and that's what we evaluate. So very, very simple. To go into a little bit more detail, the prompt that we actually sort of give to models looks like this. So we have like a really sort of brief one-line instruction at the top. The issue description is presented along within the relevant code files. And then the next slide, I'll talk about how we actually retrieve code files. And then last but not least, the additional instructions are just related to how to generate a patch along with sort of a one-shot demonstration of what a patch file format looks like. And what we find is that, since a lot of the models that we evaluate on have seen pull requests and have seen sort of issue descriptions and have been even trained on sort of code corpuses like GitHub before, this is fairly palatable to probably the best models today. But that patches is probably something it hasn't seen as much before. So that'll motivate sort of a modeling contribution. But before we get there, These are the two retrieval settings that we experiment with. So the first one is just determining like which code files to retrieve. There's a lot of extra experimentation that we're excited to do going forward, but the ones that we start off with are really simple. So BM25, just sort of the really sort of go-to standard sparse retrieval mechanism that has provably still works really well today. You might be asking, why don't we use like dense retrievers, maybe like contrivers, something like that? And the problem is that those dense retrievers have been trained on like pretty short context. So this sort of long context code-based style index that's required is really, really out of distribution with from what any of those sort of dense retrievers have seen. So with sparse retrieval, we create an index based on the entire code base at a file level, and then the issue description becomes the keyword to just sort of pick out which code documents are most relevant. So the paper has a little bit more experiments, but there's one table that kind of nails it down. We have sort of like different context windows, and I'll talk about a little bit more about that in the next slide. But what this means is that like, with different language models, something like GPT-4 has the largest context window of like 32K tokens versus I think GPT 3.5 has like 16K tokens. Claude from Anthropic, on the other hand, has 100K tokens. So what this means is like based on the model, we can only fit like so much context into each of them. And then sort of given different context lengths, what is the precision associated with like whether we're getting the correct files, or out of the retrieved files are the gold files in there. And by gold, we're referring to the files that the gold patch edits. So to sort of really simplify that, as you can see, of course, as the context window increases, like, our precision is a little bit higher and that we capture more of the files. But what we can also see is that there's a fair amount of noise that's being picked up, and that often results in the model being a bit confused. So there's plenty of work that can potentially be done here in terms of localizing edits and identifying relevant context. The second form of retrieval we do is oracle retrieval. So this is like really straightforward. We look at the gold patch, we look at the file paths that the gold patch edits, and we feed those exclusively as context to the language model. So this is the reason we put an asterisk around oracle, is because oftentimes the gold patch, the files that are edited are not necessarily comprehensive of the entire context that is required. Just as a simple example, there might be like a utils file that's being edited by the gold patch, but really like the utils is being used in a lot of different places in the code base. And to successfully make an edit, it's important to understand how that function is being invoked. So that's why we kind of put quotes around it. But of course, this setting sort of in terms of the retrieved context is a lot more precise than BM25. So the sort of second point that we happened upon is that while a lot of the current state-of-the-art models have seen issues and pull requests, they haven't really seen patches before. And structured input, as demonstrated by a lot of concurrent work, is still something that language models really struggle to cohere to when it comes to sort of reliably generating some well-formatted input. Even when there's demonstrations. So what we do is we fine-tune Code Llama, which was released by Facebook or by Meta a couple months ago, on this big SWE-bench train corpus, which has a lot of issue patch pairs to get a sort of base model to be more familiar with this format. So it's a very simple thing, but it makes a very big difference on sort of the downstream success of creating a patch correctly. So as you can see on the left, we take Code Llama, Code Llama Python specifically, so not the chat flavor or like the code flavor, just Code Llama Python at the 7B and 13B scale. We would have really liked to do 33, 34B, but due to compute constraints, we were only able to do these two sizes. Fine tune on this corpus using a sort of new library that we'll release a little bit later called Lamau, but we basically rely on a lot of current tricks like LoRa, flash attention, some multi-GPU handling and sequence processing to then create these two models, so SWE-llama 7B and SWE-llama 13. So now we can get into the results, which are pretty exciting. So in a nutshell, models are pretty bad. And then without assistance in terms of sort of the oracle retrieval, they're even worse. So the results that we're seeing here are just the percent resolved, refers to the percentage out of 2,294 task instances that were successfully resolved by a model. And again, just as a reminder, by resolve, what we mean is that a model has generated a patch, the patch was applied successfully, and then when the unit tests were run, the model's changes passed all of the unit tests. So kind of segueing into that, by percent apply, what we mean is that models sometimes actually generate malformed patches. So just the step of creating a file that can be applied to a code base successfully and have sort of changes be done correctly is sort of a barrier to entry to completing this problem successfully. So like structured format and then actually sort of having correct code are the two things that we're quantifying here. And that's percent resolved and percent applied. And as we can see, with BM25, which is probably the sort of most faithful to a very honest end-to-end form of completing this task. Even the best model gets like right around 2% of all task instances resolved. With the oracle retrieval, as we can see, there's evidence that if you're able to kind of narrow down the relevant context, then models improve a little bit more, going from 2 to 5% for Claude. But of course, even then, 5% of 2,294 task instances leaves a lot of room for improvement when it comes to sort of new methodologies that can go beyond sort of a 1/20th of task instances successfully completed. There's a couple more insights that we find is that performance differs across repositories. So what this means is that really different repositories and different use cases and different code bases really present very nuanced challenges. And by pointing SWE-bench at different repositories, there's a lot of opportunity to expose language models to different code and language understanding challenges at a sort of very granular scale. So repositories, like they have different contributor guidelines, different levels of popularity and usage styles, complexity, dependencies, all these things that make them really different. And as a result of these differences, introduce different challenges. One thing that we found was a pretty neat observation was that for the graphing-oriented PyPy packages that are present in our repository, Matplotlib and Seaborn, a lot of those issue descriptions include images, which our baseline is not multimodal and does not account for sort of digesting an image. So even solving this, I think, represents around 2% of the tasks in SWE-bench. But to be able to close those tasks, it might be really helpful to have some sort of computer vision or OCR functionality. And I think there's a raised hand.
Go on. Hi, this is Rohan. Just to clarify, can you help with the interpretation of this graph? So is the correct interpretation to say that Claude 2, which is in sort of dark orange, for requests is resolving about 15%. Your fine-tuned model, which is in light orange, is resolving slightly less, like maybe 13% or so. And then ChatGPT 3.5, which is in blue, is resolving about 2-3%. Is that sort of the right interpretation?
That's exactly correct. Yes.
Thank you.
Yeah, cool. Awesome. Yeah, thanks for clarifying. Yeah, I should have pointed that out, but yeah, that's exactly right. And I should have prefaced with GPT-4, just because it's a little expensive to call the API a lot, we run it on like a 20% subset. So for this particular graph, it's not represented. But what you can expect is mainly because of context window and because of sort of lack of fine tuning and sort of amenability to this patch format, that as we saw in the previous slide, GPT-4 performance is better than GPT 3.5, but not quite as good as a fine-tuned model or as Claude. Cool. Great. So yeah, I'll make sure to leave time for questions. So I'll go through the rest of this. Another one that is fairly intuitive is just models struggle with long context. So the graphs that we present here are the percent of problems resolved with respect to the size of the code base and the size of the issue. The size of the code base is kind of conveyed in this number of input tokens. So what that means is, if you remember from a couple slides back, that input format that we talked about with like instruction, issue, code description, additional instructions, the size of that whole prompt, we're looking at sort of the percent of tasks resolved with respect to the size of those prompts. So you can see, as this prompt gets larger, which is usually because of longer issues or longer code bases, the percent applied goes down quite a bit. On the right side, we kind of isolate just the issue length portion. As we can see there, the trend is not as significant, but there's still a small discrepancy just from sort of the small differentials in the bars. And then another thing is sort of, given that models have probably been trained on these repositories before, there is this question of whether it might be memorizing these solutions and whether if you just inflate it enough to enough parameters or inflate it to train on these and potentially overfit to these repositories, like whether this task might be rendered a bit trivial. So what we find is just from sort of filtering by date, that we don't think current models are capable of cheating by just sort of bringing up memoized versions of the code. And given that a lot of these instances are coming from different versions of the code base, simply memoizing is generally just not a good strategy to solving SWE-bench at all either. And also, as sort of the title suggests, we don't find that older tasks or more recent tasks are easier at all. Yeah. So we kind of compare performance by looking at tasks or before and after 2023, and we see that the splits are sort of fairly random, and there's not sort of a significant difference in terms of the percentage solved. Cool. And last but not least, models tend to generate shorter, simpler patches. So what we find from quantifying the model's generations, and then also sort of doing a couple of case studies that are presented in the paper, is that we find that the code that models generate, even when the patches apply successfully, when you and I look at them, there's sort of very obvious differences and very obvious areas that it lacks in compared to sort of what you or I might write when contributing to these code bases. So from here is sort of the general takeaway across all these models, and especially in comparison to the reference solutions, which is covered on the bottom as the last row of this table, is that the the generations are generally just not as complex. And when we say not as complex, what do we mean? We mean usually it resorts to primitive Python. So usually what we don't see is that while some fixes might import some functionality from pandas or from NumPy or from something else within the code base, and then leverage that to solve a problem very quickly, a model will tend to recreate that solution if it does it successfully, or write a lot of primitive Python that doesn't have much to do with the solution if it sort of doesn't work well. And then the second thing that we notice in terms of lack of complexity is that oftentimes a lot of these changes, unlike code contests, are not sort of isolated to a particular region. You'll find fixes that will edit a line here, a line there, and there's a lot of context, a lot of distance between those edits within the same file. And the same sort of reasoning and challenge applies to when we're doing multi-function edits and multi-file edits. We find that models don't really do that that much. Usually, they'll kind of target one function and then try to change that as much as possible. Some of the task instances are solved that way, but there's a good body of tasks that need to have sort of like edits across multiple steps, across multiple functions, because those edits are typically better in terms of their efficiency, in terms of not being redundant, and in terms of being sort of more readable. And then, of course, we do a lot of case studies in the paper. So if you're interested, we have 10 case studies in the appendix, but we have a quick one here where this issue, along with the code base, is from Sphinx, which is one of the repositories that we use as sort of this thing for performing documentation and linting for Python repos. And what we're finding here is with the gold patch edits a lot more, and it sort of has this very well-written explicit conditional that handles this setting within a config. So this is sort of the Napoleon use param value that's there. So basically, what this issue is saying is that the output format of a particular function should be conditioned upon the value in this configuration file. What we find with the generated patch is that the model just tries to sort of directly address the problem by changing the type of the expected output to be sort of exactly what is mentioned in the issue. And it sort of skips over the whole part of sort of being conditioned on this Napoleon use param. And we find that as a result, out of the unit tests that we gather from the original pull request, 2 of them fail. And if you sort of look at those closely, they're meant to catch exactly the case that the language model does not cover. So sort of in conclusion, kind of going through again what we introduced in this work, we kind of formulate software engineering as a task based on open source software collaboration as a sort of great paradigm of natural language issues with code-based fixes. We also collect a data set of 2,294 task instances from real issues and pull requests that have all of the components that are mentioned in the task formulation. So the issue, the code base, and then the unit tests. And while it's not mentioned here, we also have a development set of 244 task instances from 6 completely separate repositories. And then the third point, we have sort of a proof of concept model that demonstrates an sort of a novel fine-tuning approach in terms of the data that can make existing models more amenable to this task format. So that's sort of in the form of SWE-llama, along with the LaMAO library that sort of handles a lot of, or captures a lot of the fine-tuning code that we wrote to create SWE-llama. And then last but not least, our results demonstrate that, there are a lot of open problems and there are a lot of sort of benefits and new challenges that SWE-bench captures. And as a result, it could be used, hopefully, as a great test bed for comparing different methodologies around LLM capabilities. So just to spend a little bit more time kind of diving into what those capabilities could be, with a SWE-bench v2 with respect to the data set and the benchmark, there's some very clear shortcomings with it right now. It's very PyPy focused, very Python focused. So it kind of falls in line with the pre-existing problems of existing evaluation benchmarks like human eval, where they're sort of too focused on one language, in the same way that sort of multilingual pre-trained corpuses are really important. It would be great to expand SWE-bench's offerings to more repositories, more languages, and then, with more repositories comes more issue types and test types and just sort of a lot of, again, those nuanced challenges, repository level challenges that we can sort of present. In addition, scaling up the model and having sort of a more diverse fine-tuning data set is interesting, not only with respect to sort of improving the model's performance, but kind of also understanding the effect of fine-tuning. So there has been, some recent work ongoing of like how fine-tuning on potentially trajectories improves language models as agents, or fine-tuning on some format of data improves its performance on this subset of tasks. So in that respect, it'd be really interesting to sort of look at a similar sort of scaling phenomenon when it comes to SWE-bench and sort of this task. In addition, NL code retrieval is just sort of one of the avenues towards improving a model or some method's ability to scope down and scale and identify relevant context for a language model to edit. as we kind of saw the difference between BM25 and the Oracle retrieval setting. Like just getting the right files already has a couple percentage improvement. But if you have an even better methodology that could identify beyond the file to edit, the files that are affected by those edits, that would be potentially improve performance a lot too. So, there has been a lot of great retrieval work already with like Code SearchNet and, CodeBERT and Colbert being these sort of models that via encoder only or kind of encoder decoder try to create good, robust NL to code embeddings. But as we kind of observe in our work, there's still a lot of space for improvement in this area. And then last but not least, one of the things that could be interesting is SWE-bench potentially has a lot of derivative use cases. One of them being like experimenting with sort of memory as a component with language agents. You know, language models will probably expand in terms of their context windows in the coming years. But, with these code bases, it might be at least a couple of months before we can feed an entire code base into a model. So that kind of begs the question, like before we get to infinite context windows, is it possible to sort of like store a lot of the knowledge and the mistakes that a model makes when performing edits on one task instance as sort of memory that it can hold on to and improve itself with when editing the next task instance? You can imagine kind of taking one of the repositories from SWE-bench, having the model solve task instances in a chronological order and seeing like whether it's able to sort of adhere to the style better, improve, do things just generally better, as time goes on in terms of later task instances. So that's pretty much it. Yeah, I just want to give a quick thanks and shout out to my collaborators. Carlos was the first author and the lead author on this paper. I was his co-author, and we also have a great sort of set of collaborators in Alex, Shunyu, Kuxing, Ophir, and Karthik, and a lot of the people in the Princeton NLP and sort of the general research community supported us. So thanks so much for listening. I'm open to questions now. You can check out our website. We have sort of a quick description along with sort of a leaderboard. It really just contains the values that you just saw, but we're kind of hoping to sort of champion the work a little bit and try to populate this leaderboard a little bit more in the coming months. I've also sort of linked to the archive. The paper is also available on the website, and the code repository that hosts the task collection, evaluation, a lot of the model inference and model training is available within this repository under the Princeton NLP organization. Cool. Thank you.